We're recording this episode on December 31st, 2025. Normally, episodes recorded over the holidays are jam packed with science because of all the astronomy conferences. And these episodes usually are pretty devoid of major NASA news because the government holds things steady over the holidays. But 2025 insisted on not doing anything the usual way. On December 17th, Jared Isaacman was confirmed as the new administrator of NASA after what was the weirdest confirmation process I can identify. Isaacman is the youngest administrator to date. He doesn't come to the position from a role in government administration or with experience in the NASA astronaut corps. Instead, he's part of the billionaire led new commercial space revolution. He takes on this role at a point in time when the Trump administration is directing a return to the moon by 2028, when SpaceX is years behind in the delivery of the Starship HLS for lunar landings, and when China is making slow and steady progress toward their own lunar landing by 2030. And he takes on this role at a time when science and higher education are undersupported in ways we've never seen before and couldn't have imagined even 5 years ago. I don't know what to expect other than change. Traditionally, the NASA administrator has addressed the winter meeting of the American Astronomical Society. This year's AAS program is missing the typical NASA town hall, and the NASA Astrophysics Division leads are listed as giving an update. I don't know if this will change, but that session on January 5, likely before you are watching this, will be our first hint at what our new administrator will mean for the science at NASA. If there's anything to report, we'll bring it to you in our next episode. In this episode, I'm pleased to say we get to focus on science as we bring you hot Jupiters, a teardrop-shaped Jupiter-massed something, and news of objects getting torn apart and other objects getting merged together as our universe lights up the night. All this and more is coming to you right here, right now. I am Dr. Pamela, a senior scientist at the Planetary Science Institute, and you are watching Escape Velocity Space News, an independent science news show funded by you, our donors, through Patreon. Once upon a time, we thought planets formed in fairly circular orbits with rocky worlds near their stars and gassy worlds further out, and thus they stayed for eternity. Or at least until their stars' lives ended. It turns out planets can go where they want and orbit how they please, and it's up to us to figure out how the heck the universe created the myriad things we once thought impossible. Consider the hot Jupiter. These worlds are massive, and their orbits are tiny, with Jupiter-sized and larger planets orbiting their stars in hours instead of decades. We know they couldn't have formed there. The angry toddler phase stars go through would have stripped them of their gases. Somehow, they had to move there from the outer solar system. Two theories have prevailed to explain this. In one scenario, planets that interact with other planets and passing stars can end up on highly elliptical comet-like orbits. The changing pull of gravity as they bounce between near and far can then act like friction that gradually makes the orbit into a nice small circle. This is a slow process, and we can look at systems and calculate how long, at a minimum, it would have taken for a Jupiter-like world to go from a Jupiter-like orbit through to having an elliptical orbit to ultimately being on a tiny orbit. And our computer models show how this process flings any other planets hither and yon, leaving a hot Jupiter in a lonely solar system. The other mechanism for planetary migration is far gentler. We know that planets form in disks of material, and it's possible that in some cases that disk remains full enough of stuff that unused gas and dust frictionally drag newly formed Jupiter like worlds and cause them to migrate inwards. The cool thing about this kind of a scenario is you can imagine a series of planets all migrating together, allowing multiple outer worlds to survive. The trick comes in figuring out what systems may have gone down which evolutionary path. And this is where a new paper in the Astronomical Journal with first author Yuko Kawa comes into play. This team compared observationally determined ages of a variety of systems with hot Jupiters, with models that calculated how long it would take a planet to go from a highly elliptical orbit to a tiny circularized orbit. Of the roughly 500 known hot Jupiters, just 30 have ages that require the planets to have migrated through a disk rather than to have gone from an elliptical orbit to a circular orbit. All of these systems match migration models in other ways as well. They are aligned with their solar system's disks, and they often have companions. While we can't yet get at the history of every world, this paper brings us one step closer to knowing which worlds gently migrated and which worlds are more likely to have gone through a comet-like orbit on their way in toward their stars. Over time, as our observational capabilities grow, we should also be able to look at a planet's composition and see chemical evidence of a migration, as well as other hints at planetary histories. We will never know the story for every world, but over time we can understand more and more. Over the last 30 years, we've gone from not knowing if planets are common to knowing that planets can be found anywhere the material exists for them to form. And sometimes we still have absolutely no idea how that formation took place. Early in December, the University of Chicago announced that researchers led by Michael Zhang had found a gas giant planet orbiting a neutron star. And they didn't find just any gas giant. They found a gas giant with a helium-carbon atmosphere that just doesn't match anything we're used to. Actually, nothing about this system is what we're used to. Consider the shape of this world. Orbiting just 1 million miles away from a small neutron star, the planet is locked so that one side always faces its star and it's distorted by gravity into the shape of a teardrop. We've seen this kind of thing happen before, but only with stars being destroyed by their killer companions. This is the first planet we've seen like this. And the natural question to ask is, was this low mass object always a planet? Or was it once a star, but it has lost so much mass that it now looks Jupiter-like? The team behind this work, which leveraged the JWST to observe the world, thinks option C is at play. This object likely wasn't present as a planet in the original star system before the neutron star formed as a supernova. It also doesn't have a chemistry that looks like something that could be formed by stripping mass from a star in ways that we're used to. Instead, some later process had to have made it what it is. One possibility raised by team member Roger Romani is that, quote, as the companion cools down, the mixture of carbon and oxygen in the interior starts to crystallize. Pure carbon crystals float to the top and get mixed into the helium, and that's what we see. But then something has to happen to keep the oxygen and nitrogen away, and that's where there's controversy, end quote. Let me be clear. He's describing a situation where a star is stripped of material. We're looking at a core that is Jupiter-like in size, and processes, including crystallization, have changed how it's structured. With JWST, they or other teams should be able to get information on additional systems, allowing us to see if this new object is weird or just the first of its type to be observed with such a powerful telescope. For now, we have a mystery, and solving mysteries is why we do science. Our sky is vast, and our telescopes are few. This means that we are still regularly discovering new ways for stars to be born, to live, and to dramatically die. Consider the bright transient AT 2025 ULZ. Spotted by the Zwicky Transient Facility, it is located in the same part of the sky where gravitational waves from merging neutron stars seem to have originated. This kind of a merger is called a kilonova. But then the light curve changed, and it suddenly looked like a more normal supernova explosion. And researchers thought they were maybe looking at an unrelated supernova that had an awkward beginning. And some researchers looked for a way for it to be both. The gravitational waves detected by the LIGO Virgo system of instruments were consistent with one of the two neutron stars having a mass less than the mass of the sun. The only known way for such a small neutron star to form is to somehow have a massive density of neutrons hanging out just ready to collapse directly into a neutron star. In this case, a rapidly rotating massive star could have exploded as a supernova and spewed out vast quantities of neutrons, neutrons that collapse directly into a little teeny tiny neutron star. Meanwhile, the core of that originally exploding star collapsed down into a more normal neutron star. And then, those two neutron stars merged and gave off their own flash of light. Because of the lag between when a star explodes and when a supernova grows particularly bright, the gravitational waves of the neutron star merger were spotted first, and then later the supernova's following light began to dominate. This is a wild scenario. It's the kind of thing that theorists had thought maybe could happen, but now we've seen it. Maybe? We can't know with 100% certainty at this point that this is exactly what happened, but it seems to fit the data. Here's to hoping this was just the first of a new kind of super kilonova that we will see more and more of as we improve our ability to see gravitational waves and to identify associated transient light. After the break, we'll be back to look at more weird physics. Stay tuned. The timescales of galactic evolution are measured in millions and billions of years. Humanity hasn't been around long enough to see how a galaxy can evolve. And I don't think any of us plan to wait around to see it happen. Instead, we do what we do with lots of long-lived species. We look for many different examples with different ages, and we use these different aged cousins to understand how individuals are likely to change over time. This is kind of like sitting in an airport at the holidays and seeing all the myriad humans flow by. As you watch, you'll see examples ranging from the age of a newborn to the most senior of senior citizens. In an afternoon, you can capture all of humanity's ages much more easily than you could do by watching a small nursery of children grow up over 100 some odd years. What gets tricky is correctly matching the youth and adults of either galaxies or life forms. Recently, we saw a whole group of fossils get reclassified from being baby T-Rex to being a different species of dinosaur. When we are looking out through the universe to piece together a photo diary of the evolution of a galaxy, we start with computer models that run, for instance, our Milky Way backwards through time. And then we go looking for things that match each stage and shine their light from the right age of the universe. In a new paper appearing in the Astrophysical Journal and led by Vivian Tan, researchers observed 877 systems they call Milky Way twins, using both the Hubble and Webb space telescopes. These systems represent what our galaxy may have looked like across time. According to a press release from York University, where Tan has just finished her PhD, quote, "Across the entire sample, the results point to a clear pattern. Galaxies like our Milky Way grow from the inside out. The earliest Milky Way twins are dominated by dense, compact central regions. Over time, their outer parts, the regions that will later become the disk, rapidly gain mass and become the primary sites of star formation. This gradual expansion outward creates the extended spiral structures we see in present day galaxies. End quote. On one hand, these results largely confirmed our understanding of galaxy evolution through mergers. On the other hand, they revealed new facets to try and understand. For instance, they find that past mergers were more chaotic than expected, with early universe Milky Way twins showing disturbed shapes, asymmetric features, and other signatures of frequent interactions and mergers with other galaxies. In our modern universe, these kinds of violent events are much more rare, and our galaxy has been able to settle into a symmetric and largely smooth structure we observe today. This is just the beginning of what will be possible with JWST. In this study, they look back to when the universe was 10% its current age. In the future, they hope to push back to when the universe was just 3% of its current age. Additional observations will also allow this kind of work to be replicated for other kinds of galaxies, so that we can essentially roll film on the evolutions of galaxy type after galaxy type as the data is sorted and analyzed. The merger of galaxies can have a lot of visible effects. When a small galaxy falls into a big galaxy, we see galactic disks thicken up or get distorted. When large galaxies collide, well, in some cases, pretty spiral galaxies can end up looking like splatters of paint as the new galaxy's core lights up with wildly feeding black holes. Called quasars and active galactic nuclei, the bright cored galaxies aren't lit up by black holes. Black holes do not, by definition, emit any light. Rather, what we're seeing is material forming a hot, dense disk as it circles the black hole, like water waiting to go down a drain. When the density of the material gets high enough, it will light up with nuclear reactions, and this accretion disk can give off significantly more light than the entire surrounding galaxy. But sometimes, less violent galaxy interactions can also cause material to fall toward a black hole and light up. This raises the question, which process causes the brightest AGN? New data from the Euclid satellite has allowed researchers to analyze hundreds of thousands of galaxy mergers over the past 10 billion years of cosmic history. The resulting galaxies have active galactic nuclei 2 to 6 times more often than non-merging systems. Their bright accretion disks are the brightest out there, and they are associated with dust and rapid black hole growth. Team researcher Allison Mann explains, quote, "We're starting to explore just how supermassive black holes form and evolve, and to pin down the connection between galaxy mergers, super black hole mergers, and how they contribute to building up the most massive black holes in the universe." End quote. This work appears in a special issue of Astronomy and Astrophysics. One of the primary tasks in astronomy is answering the question, what is that light from? And this can be a ridiculously difficult task. Stars explode. Stars get eaten by stars. Stars illuminate gas, and gas sometimes just decides to glow on its own. The universe is full of things glowing thanks to the slow processes and the fast processes associated with the gas laws and quantum mechanics. The hardest to understand processes are the ones that are rare and don't last very long. This is because we just don't have a lot of data. But sometimes we get lucky. In September of 2024, the Zwicky Transient Facility alerted astronomers to a new blue light in the sky. Over the next 2 weeks, it would fade away. Combining pre-discovery data and new observations, the team was able to follow the rise and fall of the newest luminous fast blue optical transient to be discovered. This was just the 5th object like this to be seen, and the first object, AT 2018 Cow, or just the Cow, is a past topic of this show. Cataloged as AT-2024 WPP with a proposed nickname of the WASP, this is the brightest object in its class. Like similar objects, it is found in a galaxy rich in star formation and rich in young stars. This environment had people thinking maybe these are a new kind of supernova. But the amount of light given off by AT-2024 WPP can only be explained by transforming a large chunk of mass directly into energy. And that requires a black hole. An alternative theory had proposed that these objects are gas falling into a black hole. But this object takes that theory and accuses it of thinking too small. For perspective, the energy from this event is the equivalent of 10% of the sun getting transmuted into energy over the course of weeks. Research led by Natalie LeBaron and appearing in the Astrophysical Journal Letters shows that a binary system consisting of a stellar mass black hole and a Wolf-Rayet star could produce the observed light if the black hole shredded the star. The black hole could be up to 100 times the mass of the sun, while the disrupted star would have been more like 10 solar masses. Currently, this is just a best fit solution to a handful of objects. Over time, as more of these objects are discovered and analyzed, our theories should be confirmed. Here is to hoping for more data and more ridiculous animal names for objects. Oh, and this is your semi-regular reminder. Do not approach black holes. They are not your friend. After the break, we'll be back with Tales from the Launch Pad. Next up, I'm pleased to welcome on aerospace correspondent Erik Madaus for this week's Tales from the Launch Pad. Hey, Erik.
Hi, Pamela. On December 9th, China launched the TJSW-22 satellite into orbit from the Xichang spaceport. Let's watch the launch. TJSW is a long-standing series of communication satellites operated by the Chinese government. Also on December 9th, SpaceX launched the NROL-77 mission from LC-40 in Florida. Let's watch the launch.
5, 4, 3, 2, 1, engines full power, and liftoff. Go Falcon, go NROL-77. Vehicle is pitching downrange.
And with chamber pressure is nominal.
As is typical for NRO launches, no details of the payload were disclosed, and launch coverage was ended prior to orbit insertion. On December 12th, China launched the Deer-5 spacecraft from the Xichang spaceport. Let's watch the launch. Deer-5 is a commercial spacecraft with 34 payloads. Its mission is to provide 1 year of microgravity exposure before returning the samples back to Earth for analysis. On December 13th, Rocket Lab launched the RAISE-4 spacecraft and 4 other CubeSats from their New Zealand spaceport. Let's watch the launch.
5, 4, 3, 1.
This launch, named Rise and Shine, is the first of 2 launches contracted from JAXA to launch payloads originally meant for the Epsilon S rocket, which has been delayed. The RAISE 4 spacecraft contained 8 technology demonstration payloads developed by Japanese industry and universities, plus new copies of 4 CubeSats lost in the RAISE 3 launch failure. On December 16th, Arianespace launched 2 Galileo satellites into orbit from the French Guiana spaceport. Let's watch the launch. The satellites were the 33rd and 34th operational Galileo satellites. Galileo is Europe's independent version of GPS. On December 18th, Rocket Lab launched the STP-S30 mission from their New Zealand spaceport. Let's watch the launch.
5, 4, 3, 2.
The Rocket Lab name for this mission was Don't Be Such a Square. It got this name because the primary payload was disc-shaped. It will demonstrate operations in very low Earth orbit for the U.S. military. On December 19th, Aerospace launched the hand-bit nanorocket from the Alcantara spaceport in Brazil. Let's watch the launch.
4, 3, 2, 1.
Hand-bit Nano is a hybrid-fueled rocket, one of only a few orbital rockets used as propellant. This first mission carried 5 CubeSats. The company streamed the launch, which was unusual for a first attempt. The rocket lifted off and all appeared to be normal for the first minute or so of ascent until the stream froze, showed 1 or 2 frames of the rocket exploding, and then cut back to the launch pad. The company has not revealed the cause of the failure yet. On December 22nd, JAXA launched the QZS-5 spacecraft on an H-3 rocket from their Tanegashima spaceport. Let's watch the launch.
4、4、メインエンジンスタート。SRB3 点火、リフト。導き5号機を搭載した H3 ロケット8号機は2025年12月22日午前10時51分30秒に種子島宇宙センターから打ち上げられました。
We have a successful liftoff of H3 launch vehicle flight number 8 with onboard QZS-5 from JAXA Tanegashima Space Center at 10:51 a.m. and 30 seconds on December 22nd, 2025 Japan Standard Time.
This launch had one of the most fascinating failure modes I've ever seen in a rocket launch, and I've watched quite a few. Everything appeared to be normal on the live stream until the end of the second stage burst. It cut off about 30 seconds early. Shortly after launch, JAXA announced that the launch had failed because the second stage did not restart. In a later press conference, they showed telemetry graphs and images from onboard cameras. The telemetry showed anomalous accelerations around fairing step, followed by a gradual loss in the second stage tank pressure. The picture showed first the satellite still attached to the rocket, but with 1 or more panels missing and surrounded by debris, and then later the satellite completely gone, with only a cloud of vapor remaining. The current theory is that the satellite exploded in the fairing, damaging a propel line on the second stage, which caused it to leak. A re-entry fireball was spotted off the coast of Chile, indicating it made at least one orbit. On December 23rd, ISRO launched the first Bluebird Block 2 satellite from their Sriharikota spaceport. Bluebird Block 2 is an absolutely colossal communication satellite, 6 metric tons, and when unfolded has a huge 2,400 square foot antenna, developed to provide internet directly to cell phones. It was the heaviest payload yet launched on an LVM-3 rocket. Future satellites will be launched a few at a time on Falcon 9 and New Glenn rockets. Your final mega constellation update for 2025 is that there were 10 launches of Starlink satellites, 1 launch of Amazon LEO, formerly Kuiper, satellites, and 1 launch of SatNet LEO satellites from China. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, for 2025, the United States had 181 launches, China had 93 launches, New Zealand had 17 launches, Russia had 11 launches, French Guiana had 7 launches, Kazakhstan had 6 launches, India had 5 launches, Japan had 4 launches, Australia, Brazil, Israel, Norway, and South Korea each had 1 launch. That makes the total number of launches in 2025 330. Of those 330 launches, there were 13 failures. Reminding us that space is hard.
Before we go, I'd like to give you a quick update on extrasolar visitor 3I Atlas. This comet from another solar system made its closest approach to Earth on December 19th. From now on, it will only get more distant as it slinks away from the sun. It has been a wild half year of observing this object, and I continue to be amazed with all the ways researchers have found to repurpose spacecraft to see what they can see. Last week, we got word that NASA's Europa Clipper mission, from its position midway through the solar system, was able to look back toward the comet and use its ultraviolet spectrograph to make unique observations. This occurred last November when the comet was hidden to Earth observers by the sun's bright glare. Europa Clipper joined forces with Mars-based missions to make sure 3I Atlas was always under observation. And this mission gave a unique perspective as it looked inwards to see 3I Atlas. The data it gathered showed oxygen, hydrogen, and dust-related features consistent with what was seen from Earth and with comets in general. According to Tracy Becker, the co-deputy principal investigator for this instrument, quote, "Understanding the composition of the comet and how readily these gases are emitted can give us a clearer view of the comet's origin and how it may have evolved during transit from elsewhere in the galaxy to our solar system. What are the chemical processes at play, and how can we unravel the comet's origin in its own star system? Were these processes similar to how we believe our solar system formed? These are big questions." End quote. The team is in its early days of data reduction. When the results are published, we'll bring them to you right here on EVSN. But for now, that's it. Good night, everyone. And remember, go out and look up. Oh, and please give this video a like and subscribe so the algorithm tells you and the world when new science is ready to be learned.